Hello, this is a Foxtrot journey of payload delivery. I am Dimitry Snezhkov, work for X4Shred, officially managing consultant, IBM Corporation X4Shred, but really just work on code, application, networks, humans sometimes code. And so today I wanted to share an experience or a few things that we see out there when we do red team assessments, and some of the things that we come across and how maybe we solved the pain point that we had with creating some custom tooling, right? So if you're doing red team exercises or any kind of offensive adversary simulation, or even phishing attempts, right? Sometimes you come to realization that when you send a payload, that payload doesn't make it to the end user, let alone getting detonated. It just doesn't make it. Because you're sending from the outside, and sometimes you just can't prototype all of the things that going on the wire that stopped your payload. Could it be the link checker? If you send a link in the email, was the user able to navigate to your payload? Was it because you hosted your payload on a site that doesn't really have a good domain ranking at the time? Maybe your format or extension of your payload that you're trying to ship to the user is just not being supported, or they don't have the tools to unwrap it. And then this realization that 30 minutes after you sent your payload, you have a frenzy of sandboxes visiting your C2 server, trying to communicate with your C2 server by obviously getting the payload. So at that time, you move into operation security mode, where you basically say, well, can I minimize the attribution? Can I avoid the attribution? What do I do next? Do I create a different pretext that I send to users? My vector is burned, my payload is burned. What do? Do I recode it? So, in my experience, there are two types of customers, right, or companies. Some are very, very good with host-based detection. They use EDR on a host, they unwrap your payload, and that's how you get burned. But there are other customers that have very tight in-flight defense, meaning that the network is what burns you. And essentially, the problem of a red team here is that you really can't prototype a lot of the network defenses, because you can't prototype, solutions that are happening on the wire at that customer. While you can buy an EDR for the host, you can buy an EDR for AV. It's kind of challenging to get the same thing going for the network. So in this talk, let's go through some of the things that we've seen and how we minimize that. So strike one if we're talking about in-flight detection, is traffic correlation. Some known packets or signature of a packet gets pulled out. If you rely on your TLS by doing HTTPS or whatever custom SSL encryption you're doing, it will get unwrapped. And when it gets unwrapped, your payload is naked. You have behavioral patterns. You have a load, type, and frequency of communication to your C2 once you deploy. That, if people are actually watching on the network, gets you burned. And so what it comes down to is that if we, as red team operators, allow defenders to build a story to the point where they may not even know what that is, but if they know that it's known bad or unknown bad, or they get some form of alerting as to what they need to look at, we've already lost. So strike two is with the sandbox. Strike two is really about payload sampling. The frenzy that you've seen on your end when 15 or 30 different sandbox hybrid analysis, VirusTotal, McAfee, Falcon, doesn't matter, right, visits you and tries to analyze your patterns, that's a payload sampling. If one doesn't get you, the other will be able to get you and share it with the community. So correlation rules is if your payload actually makes it past the initial network interception. The secondary interaction is with the correlation rules on the internal network. how fast does the payload spread, where does it go, which users, or how it travels on the network. And then again, it's your submission to the cloud, to analysis engine, and you cannot use your payload anymore. Strike 3 is everything that basically surrounds your ability to deliver across the wire. It's your link inspectors, it's your domain ranking, the attribution capabilities that exist on the company, and so on and so forth. Let's minimize that. So we started thinking, what would be the improvement against certain things that happen on the wire? We know how to solve issues, to the better or for worse, on the EDR and the host, but we have no idea of what to do with the network. So primary goals for us to deliver a payload would be, obviously, it's a hostile traffic inspection, so we should not rely on TLS. We should be able to have the email or the link, if it's clicked, reach out to the external payload or external entity that basically downloads the, or if you have a stager, download the payload. If you have a payload, download some other capabilities. We should go around the sandboxes that try to repeatably sample our payload and techniques. And obviously, you know, it's nice to have attribution minimization. It's nice to be able to work through the link inspectors. And it's nice when somebody on the other side can actually use your payload, because you can create a payload that is completely passing the defenses, but it's not usable because the other side, the customer, the client, the mark, doesn't have the tools to use it. It's lacking in application support. So we started looking for things that may potentially, aid us in our quest. And one of the things that we came across was Firefox Send service. Think of it as Dropbox or Box or any other sharing mechanism that basically says, okay, drop us your file, we'll get you the link, send that link to a user that needs to get it, get the payload. In this case, we're working with a browser. We go into the browser, we're basically dropping a JPEG file. It gets somehow encrypted. It gets stored in an encrypted manner on the Firefox servers or Mozilla servers. And then the user goes out, gets the link on the other side, unwraps it, and downloads the JPEG. Seems easy. Very easy service. It gives you the link. If the link exists, you download it. If the link expires or doesn't exist, then the user can download. So we started looking at this Firefox Send private service, and we thought, okay, well, what are the advantages of solving all of our issues, or some parts of our issues, really? Well, it's built with Web Crypto API, which is a standard way of using encryption in JavaScript in browsers. And so that's how the Mozilla is able to store encrypted payload, or in this case, any kind of file, right? It's a browser encryption, symmetric encryption keys get stored in the URL, and then that URL actually unwraps it in the browser. So it's a browser-to-browser communication. Keep that in mind. The actual server is open source. It can be hosted through Mozilla, or it can be hosted on your own domain. And so here's the traffic that we actually see. The request actually goes out to the upload. You know, you drop a file, and what you get is some form of descriptor. The descriptor for the resource, and you get the decryption key in some form appended to the URL. Okay? That's what you send to the other user. In phishing exercises, or if you want to work on the inside and get your payloads from the outside, or your tools into the enterprise, that's what you will do. So goal number one was to avoid traffic inspection through the TLS, right? And so what happens here is that an exe, or a file, or JPEG, gets symmetrically encrypted, and that's what the user actually retrieves on the other end. Curiously to note that the proxy that basically does the inspection happens. So the payload travels across the hostile customer network, right? And it ends in the browser on the other side. At that point, any kind of unwrap on the TLS or proxy happened. They unwrap the TLS. They do not see anything except for the encrypted blob of data. And so the the link gets posted into Mozilla, you download the JavaScript, you unwrap the payload, and you download the file. It's very handy, right? So the proxy or traffic inspection is not in the picture anymore. We don't have to generate the shared keys either, because those are prepended and generated for us by Mozilla itself. The second goal is to actually reach for the payload from the customer network. A lot of things play towards it, but Firefox.com is mostly trusted. And so when the user gets a phish and tries to go out, all your content ranking will probably allow the user to be able to get to Firefox.com. So we started thinking, well, how do we weaponize this thing? So let's split it into three areas. The red, which is us, trying to push the payload to the customer. The green, the Mozilla, the trusted entity, the middleman, so to speak. And the blue network, which is the customer network. In this case, we've proven the two goals, right? Let's move to number 3. So we can deliver the payload, but in the event that somehow it gets flagged in the middle, maybe there's a way to fingerprint once you unwrap the TLS. How do we minimize the capability for sandboxes to actually go out to our hosting server and grab the payload? Well, it turns out that Mozilla Send server provides us with really convenient features, which are really great. They're really good for users. They're useful features. For example, you can expire the link. You can state the number of times it can get downloaded. And Mozilla gives you a very generous size limit on your file. For example, if you want to store a toolkit, 1 gig should be enough for you. And of course, you can expire it in 24 hours and be done with it. So for example, if you do not want to attack that customer, if you do not want to, the user to download that payload, you can just leave it. It's going to be gone in 24 hours. You can also forcefully delete your payload if you want to. You can put password on it if you choose to. Okay, so on to number 4, minimization of attribution. In the beginning, when we started talking about Firefox Send, what we said is that it's like Dropbox, or it's like Box, or maybe Google sharing, but it's really not. It's anonymous. You do not have to have a credential or set of credentials or user ID and a password to be able to sign up for this ID. You come in, you drop the file, and you just get a link. And every time you drop the same file, you get a different link. And every time you drop the file, you get a different shared key. So essentially, if defense gets our payload and signatures off of either a decryption key hash or maybe a resource ID, that's not going to help them. So number 5, capability to minimize response from link inspectors. Well, that's really just a good side byproduct of using Firefox.com. Firefox.com looks much better than any other site that you probably created in the past 2 days. So what do we get with this? We get fully custom application encryption. We get full support on the JavaScript because it's a JavaScript browser web crypto API. It's used by pretty much all the browsers except for Edge at this point. Probably will get there because just market pressure. So we decided to weaponize this happy file sharing service as we talked before. We created 3 tiers and we started looking into how do we actually productize that on a greater scale. So that's good and all. We can now do just manual sends. We can pretty much coerce companies to download or Marks on the other side to download the files without any kind of repercussions. We filled our initial 6 goals. But here's the thing. We really want to be able to do it fast. We want to be able to prototype it for more than just one environment. And while it's nice to do it just for that customer, we also want to do it for others because we think that, well, at this point where the red team is actually losing the game and defense is really ramping up, and we have seen really good results from defense. So we actually need to step up our game and automate things. So what would be the 3 sort of auxiliary scenarios or goals for us to do something with this service? Well, we can build the delivery framework on it. We can have a lot more challenges, dealing with task synchronization, so we have to address that. And then finally, maybe, we can build a command and control base. So we started decoupling what that service does. What are the web APIs that are so standard, and what can we do with them? You can do it with curl, of course, but it's kind of, it's not minimized. It's very, just manual. But you have a JavaScript engine, right? So we can toggle off of that. Web Crypto API is nothing more in JavaScript than JavaScript Crypto Web API plus crypto standards and HTTP libraries. So, would it be fair to say that if you port it to different language, we can actually take the Web Crypto API, use the same encryption, AES, do the SHA, whatever the case may be, apply the same HTTP libraries on a different side, and use the same crypto standards, so we can port it, say, from JavaScript to Python? Well, of course. But then the problem becomes that JavaScript, or rather Mozilla Firefox Send servers, the Mozilla servers themselves, they don't have a way to notify the other side, the agent that we want to build, what to do with it. They just toggle data. So I can store the data, but I can't tell the data to tell somebody else on the other side what to do with it. So we needed a side channel. Side channel on HTTP, then you run exactly the same issue, because you have to have ranked domain, you have to be able to age it, you have to be able to trust it, and so on and so forth. You can use ICMP, but in our case, ICMP is fairly limited because it's kind of loud. It doesn't have a lot of capabilities to do what we need to do. We can use DNS. DNS is also being looked at from defense, but the way we do it is we're going to try to split the channel from the command and the data and minimize the actual traffic. So essentially, that's our goal number 2. If we employ DNS, what do? We use a custom DNS broker, and we create a protocol, application protocol, what to do with that file, or rather a link, on a payload. So essentially what we want to do is we want to use DNS TXT record, and that DNS TXT record is going to be encrypted by the shared key provided to us by Firefox. And that's going to be a fully valid DKIM record, which upon unwrap, because we know the key, will be able to provide a URL for the payload and a specific metadata, what to do with this payload. On the wire, it looks completely normal. It looks as if any text record, it doesn't travel very frequently. It's only there to give you the metadata, what to do with the file or the URL that you're trying to get there. Master-slave concept? Sure. More than one agent? Sure. So why not just do this? Why not just have a expansion of what we want to do? The red stays the red, the blue stays the blue, the green is our trusted Firefox server, and the yellow is our DNS server. And essentially we have 2 commands and control channels. We have gone from being able completely visible to the network inspection to be able to split the command channel to the DNS and the data channel to the Firefox Send, so they cannot correlate us. We also built intervals to build in to get into that specific environment. Make sure that our efforts are not very loud. Because if you think about it, there are things that split the data on TXT records and shove maybe 1 million TXT records through the network, getting your data across. But in our case, that one DNS TXT record is just a command, is just a metadata. The data actually comes from the Firefox. So Firefox Operation is pretty simple, right? You have a master that posts the commands through the Firefox link, through the DNS, to the slave, or the other way around, depending which way you want to communicate. If you want to exfiltrate data, the roles get reversed. You may want to send the payload through exactly the same mechanism out to your C2 or out to any other communication endpoint. And everything is brokered through the DNS, right? So Foxtrot C2 is born. Foxtrot C2 is really just a mechanism to use split HTTP data delivery from DNS commanding. And on the wire, once you drop it in, it's going to look completely normal from both HTTPS standpoint when it gets a file from Firefox, and it's going to look very normal from the DNS perspective, unless you're actually watching and know exact split of that channel, right? The data goes on HTTPS and DNS only gets one packet. So what are defenses for this? Well, first of all, the vendors that deploy Firefox Send on local network, private servers, should put CAPTCHAs, if they can, on Firefox, on exposed Firefox Send server, because then we're not able to do real-time communication. We need to be able to solve CAPTCHA, right? Then they probably need to throttle the number of uploads to the endpoint. So, for example, if I type shell-like commands, I have 5 seconds delay between commands on the Firefox Send uploads, then no sensible business case would really cover every 5 seconds upload of files. And if you do, then you have to have certain specific provisioning, and you actually take you need to take exception with that. And then defense, the blue team actually now needs to expect the split protocol delivery, because it's just too good of a vector for us to utilize, because we can actually go to different, we can bounce off of different mechanisms in order to split the behavioral analytics here. So while this is all good and bad, all good and all, but I think that what this boils down to, the red team, which in this case I care about, is that payload delivery itself is not easy or hard. There's just a challenge with variables that you need to solve. Hopefully you get some ideas from this. I think that right now red teams are kind of struggling with existing tooling, and we need to create more tools to test that, because the adversaries will definitely move into split channels. And then you need to instrument yourself if you are on the defender side. You need to know what fails. You need to know your network. You need to acquiesce your network. And you actually need to know the behavioral patterns that exist, because if you see DNS TXT, for example, when you shouldn't see DNS TXT at all, for example, self-registration of dynamic DNS, that's a telltale sign for you to take advantage. So this is, this code is posted out there. It will move. Unfortunately, right now it needs to be where it is, but definitely follow this Twitter, and we'll definitely give you the final resting place of it. This is a short presentation. We don't have a demo for it, but we're going to have a wiki. We're going to have videos on its use, and you guys can take it for a spin, use it in your environments if you feel this is good for you. If you have questions, let me know. I'll be around. Thank you.